All right, let's get started. So really, today's kind of application of the Fourier transform and Fourier series. Okay, and so just to see how this would work. All right, but now we're getting into applications, right? And there is an application you probably would have seen in a introductory circuits lab where you've got 110 volt RMS sine wave, right? Oops. And we'll do 50 hertz as if we're in the United Kingdom. I'm not quite sure what their peak to peak is. But our amplitude is 155. And we want to convert that into a DC signal. All right. Now, as you recall, the way we do that is we have it in here and we have a full wave rectifier. And so you get this. Now, mathematically, a really good approximation for that is just absolute. Okay. Just hold on a second. Oh, okay, it ran. I'll come back to that. All right. So now we call this a DC because the average is greater than 0, or the average could be less than 0, where in the sine wave, the average equals to 0, right? But that's not really good for most applications to have your power blinking off and on even at 50 hertz, okay? So rather than deal with the diodes here, I will just say, oh, here's a voltage source, right? And I can call that DC, right? And so now I'm getting this, and it's actually at twice the frequency. So I want this average, but I don't want it to be bouncing up and down. Well, if we want to pass DC and get rid of time varying signals, we use a low pass filter. All right. So what we have here is the Fourier spectrum of the absolute value of a kilohertz sine wave. In fact, it doesn't really matter. You can just use 1, 2, 3 and put the scale down here to whatever you want. All right. So if I put this, if 1 was 50 hertz, 2 would be 100, and so on and so on. And so you can see here's our DC component, right, scaled 0.637. Now that's with an amplitude of 1. But notice there's no 50 hertz, right, because the fundamental frequency is 50 hertz. But you can see that the frequency is doubled and that there's still upper harmonics here, and then you can see the phase. So really, what we want to do, not so concerned with the phase, is this DC is what we want. And this is what we don't want. So really, all we do is we draw a picture, you know, trying to draw it. Oh, that's terrible. Okay. Now, sure, I've drawn this like a box, and that's not physically realizable, but you can tell this is the part of the signal I want, and this is the part I don't want. All right. Now, if I wanted a time-varying signal, in this case, if this was 50 hertz, this would be 100 hertz. If I wanted this, well, then I would put a bandpass around it. And again, you could draw it better than I'm drawing on a pad, right? You could do it like that, but that's band. That's going to be a sine wave at 100 hertz. This is a low, and we want to capture, in this case, the DC. Alrighty, how's that work? By the way, I calculated that with Python and SymP. All right. So what we have here is a sine wave. The peak is 155. That gives me the RMS of 110. And I've set it in for 50 hertz, and then I simulate it for some time. And it's even wavelengths, right? And if I press Control V in, you can see that the average is 700 microvolts, which is effectively 0, and that the RMS is rounds to 110. All right. Now, rather dealing with the diodes, I can click on V out, and now you see the absolute value of that. And the average of that, which is actually the DC part, is 98.66, and the RMS hasn't changed. RMS is you're trying to get an equivalent voltage to whatever a DC is. So if the V, so what they're saying is 155 volt amplitude sine wave has as much energy or power as in a 110 volt DC source. Right? Now we're thinking that's great. I've got a time constant of 1, right? So that should give me, that should get rid of the part I want. And we can go to View, Fast Fourier Transform. To look at that. All right. Now they put it on a log scale. V in is the input signal. Notice V out has these harmonics, and the frequency's been doubled. Where's the DC? The FFT with LT Spice deletes the DC part. Now, sometimes you can get a better idea in the linear. Right, here's the original signal. Here's our first peak. And then we have 100 hertz, and then the harmonics kind of falling off. So we don't want any of these harmonics. So really, a filter that has a time constant or a frequency lower than 100 hertz should work. Right, so in fact, I've done a time constant of 1. Let's see how that works. Doesn't work very well at all. What's going on? Well, I can see this kind of ripple, and it's rising. Let's let it run for a second. It's going somewhere, but it's not gotten there yet. Well, we could remember that, you know, our time constant of this filter was 1 second, and that meant omega naught was 1. And that meant the frequency is 1 divided by 2 pi, right? Anyway, let's try for 5 tau. So it's about almost 98 volts, which is what the average was, is what we were trying to capture. It just, by using that small time constant, it took a while to get there. The good thing is, though, if I zoom in, oops, the ripple is, you know, it's less than 0.4. It's about 0.4, the ripple. Like, well, I'd like it to be able to work faster. All right. I want it to charge up to its value faster. Let's do that. So now our time constant is 1/10 of a second. Okay. Certainly charged faster, but this kind of looks noisy. Let's see what's going on. And now the ripple is, we could just measure it. Ripple is about 2 volts. All right, now that might be acceptable for your application, right? And say I want it to go even faster than that. Well, now you can actually see it, right? Ripple's rather large. And what's going on is, before the low pass filter, the corner frequency was here. We keep moving that corner frequency closer and closer to this, and more ripple is getting through. So might take us some time, but you know, maybe well, actually, so we've got that. Well, that gives us a DC power supply, which then we can go and power op amps and digital logic and things like that. But where could the clock come from? Well, remember, on that signal, right, off of the absolute value, we're getting 100 hertz, which if we put a bandpass filter around it and then scaled it so that it became a square wave, right? We would get a clock signal. And basically what you can do is have an op amp with like a really large gain. So even if you're getting a small sine wave, that small peak will be amplified to the rail, and then you get basically a clock signal. Okay, so that's the first application. Any questions so far? Alrighty.
So are you saying adding the bandpass would eliminate that harmonic?
No, bandpass it's passing a band. It keeps the thing you want.
That's what I thought it would do, but I thought we were trying to get rid of harmonics.
Well, if you read the homework, one, I'm trying to get rid of the harmonics, and one, I need a signal. So I'm answering, there's two parts.
Okay.
Yeah, right. And then is, what if I'm trying to remove a DC signal? Oh, well, I don't want a high pass, and I just, draw something that kept these harmonics. Okay? Good question. Okay. So just to reiterate, right, that's going to give me a sine, some kind of sine wave, right? This is capturing the DC part. Now, it's time to get a little bit more into how these filters are designed, right? So we have a transfer function, and we have the numerator, and we have the denominator, and the denominator is the style, right? And you might have heard of some of these, but Butterworth is a style, right? Elliptical is a style. Bessel is a style. And the style is totally set by the denominator, and it's basically where you place the poles. And there is a unit circle, and you're dividing things up, but really the ones we're concerned with, because we're trying to make things in control, are poles on the left-hand side. All right. Now, as a quick review, NS is type. of filter. Low, high, band, and notch, right? So I can have a low, high band or a notch Butterworth, low, high band notch elliptical, low, high band notch Bessel, and then there's this other one, Chebyshev, all right? So and you know, in our simple, and if we look at the Butterworth, right, in general, low pass N of S is like something omega squared, high is S squared, notches, and band is 2. All right. Now you can have higher order filters. So a fourth order Butterworth filter low pass, this would be cubed, right? The notch, that would be cubed, that'd be cubed, that'd be cubed. This gets a little more difficult to predict. All right. But so on the project, right, we need to get what we're kind of calling the DC part, right? So that means low pass, and this is the project for the lab, all right? So that means, you know, we're just going to have this part that has no S in it at all for the numerator. And the denominator, well, you'll have your choice. You can use a Butterworth type denominator, elliptical denominator, Bessel denominator, and the Python, you just select what filter style you want by putting it in the code, and it basically spits it out for you. Okay. Now, for exams and things, I might ask you to design a fourth order low pass filter in DF2, but really for most everything else, we're going to be doing second order. And the reason, it spits out the A and the B values, right? Okay. It's in the lab manual. It shows you how to do it. All right. Now, the thing is that let's say that I had a fourth order denominator. All right. That can be kind of tricky to figure out, but that can be broken up into 2s squareds plus it's 2 damping coefficient 1, omega naught 1 s plus omega naught 1 squared plus 2 zeta 2 omega naught 2 plus omega naught 2 squared. All right. So like a fourth order is really just 2 second orders multiplied by each other. So if you know what a damping coefficient is and you can deal with all of that, well, you can deal with a fourth order. And then a fifth order would just be, you know, S plus some omega A, right? I could have a sixth order where I have another second order, then making it seventh order, I could just add in one real pole. And that's what happens, is that the first order, okay, so here's just the magnitude of the Butterworth filter. And what's great about it is that it's flat until it starts rolling off. And notice they all cross the same point here. This is all normalized to 1. And that point is minus 3 dB. Regardless of the order of the Butterworth filter, at the omega naught, it's 3 dB down. And you can see that the higher the order, the flatter this curve gets before, and then the sharper it is. So you just, for first order, let me pick something a little more colorful. Okay, you put a pole here, right? Well, that's just a first order low pass filter. So a Butterworth filter where n equals 1, right, is just a regular filter, although you could call it a Butterworth and try to be fancy, right? A second order, right, we'll try to put a pole here and a pole here, evenly splitting it, right? A third order, right, you put one pole here, and then you're trying to split that up. Now the book shows you the angles that it should be and gives you the constants that it'll be at. All right. But what I find is that it really is very convenient to use the NumPy routines to give it to you. All right. Now, in the homework, right? So here, this is the algorithm, right? You have a unit circle, and then you are putting the poles, right, evenly distributed on this half circle. All right, that's the algorithm. So what the homework is I want you to invent your own filter. And I've given an example, and so you're not supposed to invent that one. You're supposed to invent your own, okay? But this is really almost really about the algorithm, right? So what I did is I have kind of a unit triangle where I'm splitting the poles along the x-axis here. So a first order would be 1 here, a second would split it in half, a third would put this into thirds. But the complex, so I'd have one real pole and then a pair of complex poles, right? A fourth order, well, actually, I always put, in the algorithm, there's always one pole there, and then you just split evenly along the x-axis, all right? So you can come up with your own shape, all right? But you have to describe how to do it. In the homework, I give my, my algorithm. And so really, it's about describing your algorithm, okay? But it's kind of advanced, but it'll really kind of get what you're going for. All right, just let me double check. Okay, you are making something with 60 hertz. Explain how to convert a 60 hertz thing to a DC signal. Explain how to create a clock signal, and then there's a 60 hertz hum. How would you get rid of that? All right, so we have some kind of 60 hertz that we want to get rid of. We want some kind of signal that we want to keep, and we have something we want to keep. Here, right, this whole picture and explanation is I'm telling you my algorithm, all right? And I go into all that detail. So your answer needs to look like that, except a different algorithm. And sorry I keep saying that, but when I graded it last year, it seems a lot of people missed that, all right? But it's a very high level problem, all right? And so you can't really wait till the last moment to get it done, all right? And yeah, as far as an open book, open note type exam problem, that's probably a good one. So other algorithms, this is the elliptical filter, and this is the magnitude of it, where the body was flat. See how sharp it is here, right? So that's a different style. And what they do is, rather than the Butterworth going on the unit circle, they, see if I can draw this. They're doing it on ellipse. God, that's terrible. Sorry. Okay. So rather than circular, they're doing an ellipse. All right. And yeah, you get these ripples, but you also get this really sharp transition region. Okay. So now we're going to talk about the pulse width modulated DAC, digital to analog converter. And if you look, here's time, right? And this signal here is a 1/8 duty cycle signal. So it's on for 1/8 of the time. This is on for 2/8, 3/8, 4, 5, 6, 7, right? And what we do is we are trying to get the average of this. So the average of 1/8 will give you this DC value. The average of 2/8 will be here. And we actually get our stair step effect. But this is the system clock, all right? So the thing is you have to understand that this is a periodic signal, meaning it's not changing every clock cycle. It could go 10 clock cycles at 1/8, and then maybe 10 cycles here, 10 cycles of these periods, all right? And so the advantage is you can have one output pin and effectively a low pass filter, and you've got a digital to analog converter. So let's look at this maybe a little more mathematically. I need to get this out of the way. Is that pulse width modulated signals have a DC and an AC component, right? When we want to look at that, right, we take the Fourier spectrum and we can find the DC and the AC spots, right? But if I have a DC of a half a volt, and then I have a peak-to-peak volt square wave, right, this is centered at 0, and then add them together, well, then there is my 50% duty cycle square wave, right? Now, usually you don't make the DC, make the square, and then add them together. You just use a pulse, all right? So again, this is what's coming out of your microcontroller, and you want to get this part. So it's very similar to the example we did before. All right. Well, in the example we did before, we put a filter on it, right? And so we want a low pass filter. And at this particular point, the gain is 7 dB, all right? So converting that to linear, it's 0.44. So if the input is a volt, the output should be 0.44 of that. So this is just, we're calculating this out. Then we go and simulate it, and you see that a V in is going from half a volt, then V out has been reduced, and it's delayed. You have to look, it's a little hard to see here, but the phase is there as well. All right. So it doesn't look very DC, right? It still looks very like there's a big ripple. Okay. So we then change the filter, and now V out is going like this kind of triangle wave, right? And this is the sine wave, right? And that's because it's not filtering out all the AC components. And when you sum them up, it starts to look like that triangle wave. Where with the normal Bode plot, we're saying there is a sine wave here, a sine wave here, a sine wave here, a sine wave here, a sine wave here. But for a pulse, well, it's our spectrum. Oh, sure, we have the fundamental frequency, and then we have the third harmonic, fifth harmonic, seventh, on towards infinity. So in fact, you don't get just the sine wave. It's actually, you get something bigger. All right. So if we, again, change the filter to get rid of more of that signal, well, now you see this kind of triangle ripple. So we're getting rid of more of that. So it's centered around half, but it's rippling. Now let's just take a quick picture of that. So this ripple I've drawn it a little larger, but inside here it's rippling. So you don't really, you're uncertain as the voltage inside that ripple. So the way I've drawn it though, so that uncertainty divided into the whole voltage range is how many bits you would have. All right, so loosely speaking, right, if all of these had the same height, right, I'd have 1, 2, 3, 4, 5 regions, right? That's 5 digital things. So if I take the log of 5 divided by the log of 2, that gives me my effective number of bits, all right? So if I want more bits, I need to make this ripple smaller, all right? So if this is my first harmonic, and that's my third, right? And that's omega C, the cutoff, right? The more I move this way, the more these will be attenuated, all right? So if I were out here, it never goes to 0, but it would certainly attenuate it more than this. However, this is your usable bandwidth, right? So if I keep moving this farther and farther, or closer and closer to 0, the more and more it will behave just like a DC power supply. Where, right, if I wanted to listen to music digitally, right, I got to be able to play 44 kilohertz. So that's what my filter would look like. And then my harmonics would have to be out there. All right. So one thing is we need to reduce that ripple. The other thing is we need to have more clock cycles as well. So if we come back here, we have a clock cycle that we can break up into 8 periods, all right? Well, if we had a clock cycle that we could break up into smaller periods, right, we'd get more bits. And so there's actually, will be 2 things, is that this, like the slower the pulse width modulated signal is, the more bits you get. Well, with the filter, the higher the harmonic, the better it is. They actually work against each other. And so here's a, this is not a Butterworth filter. It's just a second order filter that you can see the ripple's even smaller now. So that ripple, I could divide in to all of that and get the effective number of bits. Now this is me zooming in on it, right? And I could keep reducing the ripple by adding more stages and moving the cutoff frequency farther away. All right. But here's the equation, is that if I take the voltage swing max, in this case it's 1 volt, divided by the uncertainty, the ripple, and get 100, right? The effective number of bits just due to the filter is 6.64. All right. But that's not the whole story. Is that you have a clock frequency and you divide that into your pulse width modulated frequency. And so what happens is you want this to be really small, right? But this cutoff frequency you want large. Okay. So in this case, yeah, we get like 0 bits. But it's a nice, easy thing to calculate. This is the log of the fraction of the clock frequency. You can just see that this linearly goes up. But that's not good enough. You actually have to do both, where the blue line is due to the filter, and I'm automatically measuring the ripple versus frequency, and then I'm just calculating the number of bits due to frequency, and then you take the geometric mean, and right there will be your maximum effective bits and the frequency at which you should run your pulse width modulated signal. All right, and that happens to be a second order filter. Okay. So just for example, we've got a low pass filter here. We're going to do the step response, right? And we see it goes up and it comes down. But notice we're giving this enough time to rise all the way up and rise all the way down, right? This here would be the frequency of the pulse width modulated signal. It's not the duty cycle, it's just the frequency of it. And so if we start turning that off and on faster, right, you can see that it's starting to ripple up to its average spot. Okay, and that's just like the example we started off with the power supply, where this time constant to come to here is the same as the same time constant that you would use to calculate it, as if it was just a step. Okay. The difference is that because it's 50% duty cycle, you're going to the average of half whatever the input was. And yeah, you can zoom in on that and you see here's the ripple. You measure that, put it into this equation, all right? And then you can say, oh, right there, I'm getting 5.56 bits. This basically, I'm trying to show you that in order, you know, why am I always talking about 50% duty cycle? Because 50% duty cycle causes the worst ripple, right? And so at 75%, the 75% duty cycle ripple will be smaller than the 25%. So in fact, all you have to do is find the ripple at 50% and everything else will be better. All right. So it's rather lengthy. So what I'm going to do is I'm going to just show you the Fourier spectrum of the hold on. Sorry, that was I had a different example. Okay. No. No. Okay. So here's our. So this is the spectrum of a 50% duty cycle. Doesn't really matter whether it's a kilohertz, right? That's the first harmonic. Second is missing. Third and fifth are there. The thing is the reason why this gives the worst ripple is these phases are all in line. And so when they'll each be at their peak, right, at the same spot, even though they're, you know, multiples of each other. And so you're going to get the peaks adding. All right. So if I do 75% duty cycle, notice the average is now 75%. Yes, these coefficients are less, but I've got more of them. But notice this is at 45, minus 90, minus 45. So these harmonics will be out of phase, and so they just don't add as well. So really, it makes it easy, because in order to test this, you only have to put in 150% duty cycle square wave, right? And you can go from there. Now, yeah, what would the low pass filter look like? Well, I got to have a low pass filter in here that's trying to attenuate all these harmonics. Now, yeah, these are pretty close, right? And so the higher order the filter, the sharper the line. All right. Now, in these notes, I've said that, in fact, this is really impossible to simulate, to come up with a hand calculation. I've actually so what's going on here is that, and today isn't about showing you how to run that file, but basically you come up with a filter and you just keep changing the pulse width frequency and measure the ripple. And then you calculate what happened, and you get a plot like this, and it tells you. And you kind of don't know what you're going to get ahead of time. Well, in fact, I did find a way to calculate it. And that basically, you tell it a Butterworth filter, make some assumptions, tell it the frequency and the clock frequency, and it'll just tell you the effective number of bits. There's a lot of code here, but bottom line, it'll tell you the effect. You know, this is the first order, and it'll tell you the frequency to operate at, and you can see that the number of bits increases with the order. The frequency is allowed to get smaller with the order. But notice you go from like 3.6 to 5.6. It gets smaller the more you add. So at some point, there is a limiting factor. And that limiting factor is this red line. No matter how sharp you make this, right, that's going to be you can't go beyond that line. All right. That's pretty much it for today. So now what we can, so what I've got an activity all set up. Sorry, I'm just trying to. Okay. You guys, teach. So let's go to the breakout rooms. Today, I'm going to try to break it into groups of 3, right? I'm just going to randomly assign you, go in there, and it should be module 27, and it'll be another system ID. Okay, so let's start that. So when you're done, yeah, leave your room and come back, and you can ask questions. If you have any questions while you're doing it, just chat. We'll do that. Sorry, forgot to open up the rooms. Hey guys, there seem to be a lot of people here who don't seem to be participating. I see Andrew, Ong T, Carolyn, Colby, Jonathan, Austin, Patrick. Right, please join your group. Carolyn, can you join your group? Ong T, Fred, because some groups only have one person.
I don't think I can.
Is this Carolyn?
Yeah, sorry.
Oh, why can't you?
I think, so I was in one and then I got like kicked out of one, but the way that I got in was I accepted an invitation from you to a breakout room. Would you send another one? Oh.
It's room 12.
I see at the bottom I can join breakout room here.
Sorry. Fred, you there? Ong T? Ong T, Fred.